Hello everyone. Today we shall see an interesting way of determining the temperature. Normally we know that the temperature is measured using a thermometer. That is, we place a thermometer in contact with the surface whose temperature is to be measured, and the thermometer records the temperature. Maybe some 20 degrees Celsius, 30 degrees Celsius, whatever is there, that thermometer will record it. So this is how we normally determine the temperature of a surface. But is it possible for us to look for the temperature or estimate the temperature without having its physical contact? Is it possible? For example, we want to measure the temperature of a star, distant star. Measure the temperature of the sun's surface, solar surface. So we cannot take our thermometer and place it there. On the other hand, it is possible for us to measure the temperature using some indirect methods. Probably by this time, all of you might be knowing that we're using thermal sensors. Whenever you go to some other place, so they will just hold this kind of thermal scanner at your forehead and just see there. Now, this particular instrument will not be in contact with your forehead, will not be in contact with your body. On the other hand, that can estimate the temperature. So, how it is possible? Let's see the basics of this using a simple concept of radiation. Okay. Now, what do you mean by radiation? Radiation is an interesting phenomenon available with associated with the heat. Suppose an object, or say my body, is at a finite temperature, then that starts emitting certain rays, and these rays are called thermal radiation. Now, there is a very interesting phenomenon of the analysis of these thermal radiation. Just look at this graph. So here in this graph, it's a graph plotted with the energy density with this function of the wavelength of the radiation. So actually this is a black body radiation spectrum where this is the energy associated with a given wavelength and we plotted as a function of wavelength. Now you can see a Maxwellian curve like this. It increases and again drops down. Now, at a given temperature, we have a characteristic curve like this, and this curve has a peak at a particular wavelength. Now, this first curve, curve number 1, is having a peak at lambda 1. Now, what is the meaning of this? Actually, this lambda 1, which is the wavelength corresponding to the majority of the energy, or whatever wavelength here available, so they correspond to some energy, but this one lambda 1 corresponds to maximum energy. Or we have more number of waves corresponding to that wavelength. We call that as most probable wavelength. So lambda NP. Now, if the black body is heated to some other higher temperature, then we get a similar curve, but curve of a different nature. Look at this part. This is curve number 2, which is being plotted in the same way, but of a black body at a higher temperature. Supposing you call this as T1, then this is obtained at a temperature T2, which is more than T1. Now, what is so interesting about this? When the temperature is more, the curve pattern that changes. More interestingly, the most probable wavelength will change. So the most probable wavelength now becomes lambda 2, which will be moving closer to the shorter wavelength. Now, interestingly, we have a very simple formula, often known as Wien's displacement formula, which says that lambda into T, or lambda most probable into T, is a constant. Where this is Wien's constant. Now, this lambda m, I'm just coming to that point. Please be careful to listen to this. This lambda m, most probable wavelength, thus is a characteristic of the temperature of the surface. Now, this thermal scanner or any radiometer, what it does, it absorbs, it receives the energy, receives the radiation coming from the substance, and it just analyzes that and looks for the most probable wavelength in that radiation. And the most probable wavelength, since it is a function of temperature, since lambda equal to T is equal to constant, by knowing the constant, I can have an estimate of temperature. Suppose the body whose surface is say feverish. Now say my reading say 95 degrees Fahrenheit. Now supposing a person is having a high fever and if this scanner is pointed towards him, then what will happen? Then you notice that there is a sudden rise here, and there the most probable wavelength corresponding to that will be of a higher region, or will be of a shorter wavelength region, and thereby by having an estimate of lambda m, it is possible for us to estimate the surface temperature. So this is how the Planck's radiation law will help us in a very interesting way to locate the temperature of a surface without having any physical contact. Thank you.